So the first thing is to give you a little story about Wacoit Bay and what the changes have been there. And, this is kind of on this topic of a lot of people in this room collect data, right? And ultimately doing something with that data and providing meaningful insight with that data is what we really need to focus on. And that takes time and funding, which we often don't have to do that. So, when you think about all this data collection, and it's a larger problem in the larger world with social media and news reports and that kind of thing, really thinking about why you're collecting data and what you want to do with it is really important. Restoration is all about location, right? If you don't address the underlying problems that cause the need for restoration, you're never going to be able to fix the problem. So you can go out and plant as many seeds or as much seagrass as you want, but if you don't address those underlying challenges, you're not going to be successful. So that's a really important point about any of the restoration efforts that we do. First, I'm going to talk to you about the location of Wacoit Bay National Estuarine Research Reserve and what the story with eelgrass is there. I'll talk to you about a project that kind of started as a side project, student projects, just kind of a crazy idea that we wanted to test out and see if it works or not, which is the Seagrass Meadow underwater restoration platform. And finally, I'll talk to you about another location of Little Pond in Falmouth that was fully sewered in 2016. So we're a decade beyond the mitigation efforts there. So, providing a little bit of context from a local case study in Wacoit Bay. So why did all the eelgrass disappear in that location? And you've seen a lot of maps from both Agnes and Myrta, but this is one that goes back all the way to the 50s. We know how much eelgrass there was in Wacoit Bay on the lower left on that side. Coming across the years, you see a steady decline throughout the bay. In 2015, the last sort of spots of eelgrass were in Sage Lot Pond. That was a small pond that researchers at MBL and Hui and other places had used as this pristine research site. And eventually all the eelgrass even disappeared from that location. In the upper left, that's bay scallops harvest. Anybody that's interested or enjoys eating bay scallops, as the eelgrass disappears, the bay scallops disappear. There's a very tight association between those two, so you can see how the harvest has dropped off there too. So if you don't have this ecosystem structure that the canopy of seagrasses provide, you won't have any bay scallops. So here's really the big issue on the Cape, right? 85% of the households on the Cape use septic systems. We're actively trying to address this across all of the towns right now. It's a massive infrastructure project. And you can see sort of the start of this in Falmouth with the red sewer lines. Little Pond, the one I'll talk about there, is the little orange region that you see was recently done. But when we're looking at Wacoit Bay here, which falls on the Falmouth-Mashpee town line, are we going to get there in the 2040s, the 2050s? And what do we do in the meantime? So I teamed up with wonderful people at Webner and with Jordan Mora, who's now at APCC. We went through all of their long-term data that they've collected, in some cases going back to the early 90s. And what this is temperature anomalies at 3 sites within Wacoit Bay. And that's just a statistical analysis to look at the trends of warming over time. So this is plus 1 degree Celsius over 20 years. This is global warming right here, all right? If you combine that with some other records that were estimated off of Woods Hole, it comes out to about 4 degrees Fahrenheit, 4.5 degrees Fahrenheit. In my lifetime, these waters have warmed here, right? So very clear in the data. So this is more of a global stressor, not the local stressor that we talk about when we talk about septic systems. Looking at dissolved oxygen, we're breathing it right now. All the organisms in the water need that too. That's declined by about 11% over the last 20 years. And for anybody thinking about gas physics, that's not just the temperature signal, right? This is driven by eutrophication in the system. These extreme events are becoming more common and lasting longer. So on the left over there is heat waves. And we see that they're increasing and lasting longer. Top right, we have hypoxia. So this is low oxygen conditions that can harm any of the organisms and exclude them from the environments. And then on the bottom right, these are harmful algal blooms. This can be cyanobacteria. This can just be pelagic photosynthesizers living in the water column, we see those have increased over the last decade too. So there's this combination of both local and global stressors that are affecting our estuarine water quality. And that ultimately is at least part of the reason that eelgrass is no longer persistent in McCoy Bay, which I remind you is a National Estuarine Research Reserve, right? This is a place that we should have eelgrass growing. So really what's happening here is we have too many nutrients in the system. I can plot this a dozen different ways. You see they're all increasing, right? So what's happened over the years is the amount of total nitrogen in the top left has increased. We can graph that against chlorophyll. Chlorophyll is the photosynthetic pigment in eelgrass, but also in phytoplankton that live in the water. And what you see is this relationship between nitrogen and chlorophyll A increasing across a number of sites, across different citizen water quality monitoring programs, across Webner's data itself. And really what this is a shift from benthic primary production on the bottom by first seagrasses, then by macroalgae, and now by green stuff in the water column. So this is why your water looks turbid. This is why it looks green. This is sort of the terminal stages of eutrophication impacts in a local estuary here. So what that means is all of that stuff gets washed in and out of Wacoit Bay on every tide. What that means is a place like Sage Lot Pond that previously was still in pretty good shape because it had a very small watershed. Now that pelagic biomass that gets transported around with the tides is going into Sage Lot Pond and degrading it there so that eelgrass can no longer live there. So you get this mobile biomass that is harmful throughout the entire estuary. So that's kind of the story of how eelgrass got excluded from McCoy Bay. And now, obviously, we're trying to fix that with installing sewer systems, but also we kind of need ways to give that eelgrass a jump start to be able to start re-inhabiting those areas that we previously degraded. And this is an idea that me and my lab members came up with, the Seagrass Meadow Underwater Restoration Platform. It's got a cute name. Everybody can remember it, called the SMERP. And the idea here is we bring eelgrass up closer to the water surface, right? Light is a major factor that excludes eelgrass because you have that green water. So we bring it up closer to the surface. We work with methods like Meadow was just talking about by growing seedlings in the lab, getting them sprouted. We can have much higher germination success rates in the lab than we can in the field. And we can put these platforms out and grow eelgrass in them, sort of in this semi-modified environment. And the idea here is, okay, this environment is really impacted. How can we kind of engineer around this eutrophication problem that we have to grow eelgrass? And the idea here isn't to put 10 million of these things out in the estuary. The idea is to make a well-developed turf of eelgrass that we can then put in the appropriate location. Going back to that location, you have to put it in a place where it's going to be successful. So now I've got a good growing mat of eelgrass that has a much better chance of surviving adverse conditions than, say, broadcasting seeds by throwing them off a boat. So this is the idea. Okay, these locations have issues. Can we modify the site to be able to give this eelgrass a jump start to be able to re-inhabit those areas? So we tried a million different things. We tried to grow seagrass hydroponically. That didn't work very well. We tried using different sediment types, different coconut core fibers to stabilize the eelgrass. We did open-sided milk crates to let water flush through the sediments. And ultimately what we found out with is just a regular tub of dirt worked best. So we tried all these things and nature had figured it out long before we tried to modify it. And the best way to do it is just in sort of a natural sediment system. One thing that was very important as I started doing this eelgrass restoration is people love eelgrass, they love talking about it, but they don't really care about it until you address the problem, right? So we kind of had to have a eutrophication nutrient angle on all of this to enable this research to continue forward. So what we did and what we were trying to do with all those different treatments was try and enhance rates of denitrification. That's microbial conversion of inorganic nutrients, inorganic nitrogen into nitrogen gas. That's 78% of what we're breathing right now. So it effectively moves those nutrients from the system. And what we demonstrated here is once we get the grass growing in that crate, it actually enhances denitrification rates. So that gives us an angle that we can go to managers, to town officials and say, hey, look, we're growing eelgrass, but this also addresses the local nutrient issue too. So sort of our first field test, we did this in Little Pond, which was sewered in 2016. We're now just starting a decade later to see recovery in some of that system. And that's the first place we took this system to try it out. We planted some very small shoots in that crate, and by the end of the year, we had a 5-fold increase in the number of short shoots, and the biomass was just massive compared to what we started with. So the idea that we can put this system out and grow grass in it, great, all right? You should be able to grow grass. It's all right, it's kind of a weed. If the conditions are right, it'll grow. So we kind of went to scaling this up. We went back to Webner to try out that Sage Lot Pond site as well as another one. It's difficult to see, but little tiny grass shoots there, suspended in coconut core fibers. That's my student Samuel prepping one of these systems. We had a whole bunch of sensors on there to understand what's going on in the water with light as well as temperature and salinity. We're trying to standardize this. We're gung-ho, ready to go. And for whatever reason, 2025 was not a good year for our system. So we're still trying to dial this in. We were pretty sure that our shoots were just too small. So we're trying to grow them up a little bit bigger in the following years and this year before we put them out. So that's kind of what it looked like later in the year. We had a few shoots, but nothing great. You can see a lot of sort of green water in there, brown water in there, a lot of biofouling. So we're still trying to dial the system in, and we're doing that by growing bigger shoots this year in the lab before we put them out. So a little bit of what we've learned so far. Don't try and grow seagrass hydroponically, even in high nutrient systems. It doesn't work. So saving you time on that experiment, hopefully. Seed germination is highly variable, as Myrta talked quite a bit about. We think that shoot maturity is really important for our platform and having it work out in the field. We've shown that we can enhance denitrification in this sediment bioreactor platform, and that kind of addresses the local issue to gain traction on getting more of these out in the field. We're working on scaling this up. So now we're working with 3D printing biodegradable materials that we can actually make our platform out of, so we can take it right off of our buoyancy system and plant it right in the ground and just make it much more efficient. The idea here is to really create that established turf of eelgrass that we can plant out that has a much better chance of success than just putting out seeds or shoots. So the other side of this is outreach and advocacy, especially for eelgrass, our water bodies in general. These are a variety of local and national news stories. Secrets of Seagrass is a PBS documentary that we were recently featured in. So the outreach portion of this and talking to groups like this is a really important aspect of what I do, getting the word out there about how important these ecosystems are and how important the health of our coastal estuaries is. And I would like to thank everyone that helped me with this and the funders. And the last thing I would like to leave you with is a video that my student Samuel took when he went to Block Island. And he was super excited and sent me this video and said, look how healthy this eelgrass looks. Look at all the healthy algae that's growing on the rocks next to it. He's like, the water was clear. And I was like, that's what it should look like, Sam. Right? This is what we should have in our coastal estuaries. We should all be able to go snorkel in them and see this. So, to give us something to strive towards, to improve our ecosystems, this is really where we want to get to, just so we don't lose that baseline of what it should look like. Thank you.
Thank you. We have time for one, maybe two questions.
Thank you. You mentioned Long Pond, and I grew up in Falmouth. I grew up right on Mary Vista Ave, so I spent a lot of time on Great Bay as a kid, and there was quite a bit of eelgrass when I was a kid. And I just remember Little Pond as being a mess when I was growing up. And I'm just wondering, and I know you mentioned that area was recently sewered, but how did you pick that location? Is it a location that would be ideal for this? Because I don't ever recall that area being even remotely healthy. And I'm just wondering how things have
Yeah.
gone so far.
A lot of houses around there, very sandy sediments. Every house was on septic systems until 2016. So I can imagine it was really bad, and it's still not great. It's still pretty bad, but there was natural recruitment of eelgrass into that system, and there is natural eelgrass beds there. And with the fact that we've seen declining nitrate levels in the groundwater, we kind of said, we now have this really unique study where we can say, look, this is a system we've actually improved. What does restoration success and that reversal of eutrophication actually look like? And that's an experiment we don't get to do very often, right? We get to do the other way when it gets worse. That's the experiment we get to do. So it's kind of a unique opportunity, and hopefully we have a lot more of those going forward.